Good morning, guys. Please welcome to the second session this morning. And the first speaker in the second session is Stéphane Seuret from Université Paris-Est, Val-de-Marne. And he will speak about multifractality and additive stochastic processes. So please welcome.
So thank you. So I thank the organizers for their kind invitation. And also it's my first conference outside of France for 2 years, so I'm quite happy to be here. So I'm going to talk about multifractality and stochastic processes, and especially additive stochastic processes. So let's go so straight to the point. So what I'm interested in is the variations of the pointwise regularity of the trajectories of a stochastic process. So this kind of question can be asked not only for stochastic processes, but also for functions, for measures, for two-dimensional objects. And also, so here it's so here it's the deterministic Fourier series. Here it's a measure. Actually, it's here. So here are two examples of stochastic processes. This one is a Markov process, and this one is random cascade. These two ones are data that are collected from turbulence here, and here are two brain signals. And the idea is that, of course, these objects may be irregular. So they are irregular, but their pointwise regularity also varies from one point to the other. It's not the same one. It's not like a fractional Brownian motion. So how do we measure this? So X will be a locally bounded function for me. And so I consider alpha and a point t0. And so the local regularity, the pointwise regularity, is measured through the Hölder exponent. So I say that X belongs to the space C alpha at T0 if, well, xt minus xt0 is less than ct minus t0 to the alpha. So it's very comparable to the local regularity described by Astrid a few minutes ago. So this holds for alpha less than 1, but when alpha is greater than 1, when it produces instead of the value of x, a polynomial, which is essentially a Taylor polynomial. And we say that xt minus this polynomial is less than ct minus t0 to the alpha. Okay, and so that means that x belongs to C alpha. So if alpha gets larger and larger, then the x is closer and closer to a polynomial. So that means that f is very smooth around t0. And so that gives the natural definition for the pointwise Hölder exponent, which is the greatest, or actually the supremum of the alphas, such that x belongs to C alpha at t0. So if hx is large, that means again that x is very smooth, it's close to a polynomial. Okay. While if x is small, it means that there are very wild variations of x around t0. So of course, if you think about the Brownian motion, you can think that this hx is a constant function, but actually it may have very wild variations. But if you have working with a stochastic process or a measure, for instance, which is invariant by some dynamical systems, it's likely that there will be an exponent which is almost sure, in the sense that for Lebesgue, almost every point, there will be one typical regularity. But that does not mean that there will not be other regularities. And these other values, they may exist. Of course, the set of points having these other values as a pointwise Hölder exponent have Lebesgue measure 0, but they do exist actually. And so the way to describe them is to introduce what we call these Hölder sets. So it's not very complicated. Actually, we just say, okay, let h be a positive number, and I look at the set of points, the set of t's, such that the regularity, pointwise regularity of x at t is equal to h. And I want to find all the possible h's for which these sets are not empty, and then I want to measure the size. And since I explained you that essentially there will be one point one exponent that will have Lebesgue almost values, the natural quantity that will allow us to distinguish, to really measure the size of this set is the Hausdorff dimension, okay? Because essentially, except one H, essentially all these sets will have Lebesgue measure 0, but they may have a large dimension, okay? So essentially, a multifractal spectrum, a singularity spectrum, it looks like this, okay? So you have, it's an H, and you have the dimension, so it's less than D. And for every H0, you have a point, which is the value of the Hausdorff dimension of this set of points, okay? And maybe sometimes there is no point, like here, so it's minus infinity. It just means that the set is empty, right? And for reasons that I will try to explain you, actually, one does not expect any shape for the multifractal spectrum. It's really natural that we have a concave shape. This comes from formalisms, either thermodynamical formalisms, or also large deviation considerations, essentially. That tells you that the shape must be concave, like this is concave, like a bell shape, or something degenerate, like a fine segment here. So what I'm going to give you is now examples of the multifractal properties of stochastic processes that you know, Levy processes or other examples of Markov processes, okay? So there are two main families somehow of multifractal processes. There are the additive ones and multiplicative ones. So I will focus on the additive ones today. But actually, let me also mention that it's possible to combine these two processes by time subordination. So I mentioned that because in the topics of the conference, there are Markov processes and also time subordination. So I will talk about these two things in the next examples. So I will review quickly 3 examples. So the Levy processes. So it's an old result now, the multifractal nature of Levy processes, and I will also talk about Levy processes in multifractal time. I will also review the multifractal nature of some jump Markov processes, and explain you very rapidly also what we obtain for sums of random pulses. But before giving the examples, what I would like here is to give you a hint of the proof of the ideas that are used in this kind of in these studies. And the main idea is that the pointwise regularity of these jump processes, they essentially at a given point depends on the approximation rate by the jump points. So that's what I'm going to do to explain it now. So for this, I will consider a typical example, right? A sort of archetype example of stochastic process, not exactly of a jump process. So for this, I consider a family of couples, Tn lambda n. So Tn will be the jump points, and lambda n will be the size of the jumps at every Tn. Okay, and I assume, otherwise it's quite it's not very interesting. I assume that the lambda n tend to 0. And so I assume 2 conditions. The first one, that the sum of the lambda n is finite. Okay, and I also assume that for some beta, the lim sup of the balls, so this is the ball centered at Tn of radius lambda n to the beta, is R+. So that means that every point T, every positive T, belongs to an infinite number of balls centered at Tn and of radius lambda n to the beta. For instance, if you take Tn lambda n as a Poisson process in the upper half plane, this will work essentially if you choose wisely your parameters. Okay. And so with this, I can build the additive process xt like that. So xt is just the sum of all jumps which occur before t. Okay, so it's the sum of the lambda n for where Tn is less than t. Okay, and so I want to analyze the local irregularity of this xt. And what I'm saying is that since, so you remember my condition, every a point t belongs to an infinite, any point t belongs to an infinite number of such balls. Okay. So when t belongs to btn lambda n to the beta, it means that one of the two increments of x around t, so either xt plus lambda n to the beta or minus xt, or so this is the right increment or the left increment xt minus lambda n to the beta. One of these two intervals contains tn. So one of these two increments is greater than lambda n. Okay. And so for a fixed t, this happens for infinitely many integers, n. And so computing the pointwise order exponent, so it's the formula that was used this morning. So you replace, it happens for every n. And so you make the quick computation and you find that the pointwise exponent is less than 1 over beta. Okay. And so this happens for every t. So it's a uniform bound for every t for this process. Okay. So for every t. But actually what I claim is that for free, we can have more. So for that, I call A delta the lim subset of the btn lambda n to the delta. So the same balls, except that I contract them, right, by a factor delta. So the assumption is that A beta is R plus. That was my assumption. But actually, every point belongs to A beta, but maybe some points belong to A delta with greater delta, which they are closer to the jump points. But that's why I define the approximation rate, which is the sup for a fixed t. And so I take the greatest delta such that t belongs to A delta beta. Okay. And by construction, delta t is greater than 1. And if delta t is great, it means that you are very close, infinitely often, to the jump points. And the exact same computation as before give that actually hx of t is less than 1 over beta delta t. Same computation. Okay. And so what is quite interesting is that if the system of points is well distributed, actually there is equality. So in the sense that the pointwise regularity of x at t is exactly given by the approximation rate. Okay. And so remember that what I'm trying to compute is the Hausdorff dimension of this set, the set of points for which the regularity is h. But since the regularity is 1 over delta t beta, at the end, it amounts to computing the dimension of the set of points for which the approximation rate is fixed. So initially you wanted to study the pointwise regularity of stochastic process. Then at the end, you want to compute the Hausdorff dimension of set of points that are well approximated. Okay. So the main idea is that if you are close to large jumps, the delta t is large and your regularity is poor. So now if you have such an additive process, what's the general method? You find a suitable family of remarkable points that rule the regularity. Then you prove that this family covers the interval. And so this is called the Dvoretsky, so for random families, it's called the Dvoretsky random covering problem. It has been studied by many people, right? And you also prove that this family is nicely distributed, not too many overlaps between the balls and so on, okay? And for each t, you identify the value of delta t. And then at the end, you want to apply what is called a ubiquity theorem or mass transference principle, which allows you to compute the Hausdorff dimension of the set of points approximated at a given rate. So these theorems are theorems like that, tells you, so this is the assumption. So you remember my assumption was that this lim sup was equal to R. So actually we can weaken a little bit the assumption. You just said that the Lebesgue measure of this lim sups is 1 if you're working in the cube. Then this is a deterministic theorem. As soon as this is true, then for every delta, the lim sup of the contracted, so sorry, it's Tn. So the lim sup of the contracted balls has Hausdorff dimension at least 1 over delta. And again, the inequality is an equality if you choose well your parameters. Okay. And so the conclusion is what's the conclusion? So you wanted to compute this, the dimension of this set. So as I told you, it's the set of points for which the delta t is 1 over beta h. So I apply this. So it's in dimension 1. So it's 1 over beta h. So it's beta h. This explains the shape that the linear shape that I gave at the beginning. Okay. So now you have everything in hand. I can just give the results. Okay. So first, I'm sorry in advance for not being exhaustive on all the people working in this area, right? So the first historical result is about Levy processes. So it was, so Jean Berthoin worked on that, and actually the final result is by Jaffar. If you take LT, a Levy process of index beta, and I assume there is no Brownian component, it's not complicated to deal with it, but I assume there is not, then what I showed you actually applies essentially in the, at least intuitively, is that the Levy process, almost surely the multifractal spectrum is linear with slope beta, okay? Beta being the parameter. So it's quite interesting because actually it's a deterministic spectrum that does not depend on the trajectory, right? And then there's a whole range of possible exponents. When beta is less than 1, there are differentiable points. And essentially, what I explained you before applies almost directly, right? So this is for the Levy processes. So now I can also I want to explain what happens if so let's say more recent results. So the first one is the Levy processes in multifractal time. So you can so the set of jump points for the Levy processes are homogeneously distributed in time. Okay, and it's very interesting to modify a little bit to add some heterogeneity in the distribution of the jumps. And how you can do that? So you consider so L is still a Levy process, but instead of T, you put f of T, where f is the integral of a measure, right? And in particular, so f is not a subordinator because, well, in our case, it does not change a lot the nature of the process. But the main examples, I don't know if you know that, it's like it can be a Gibbs measure invariant by a dynamical system on 0, 1, or it can be a binomial measure, or it can be a cascade, Mandelbrot cascade. I don't know if you heard about this. Essentially, you modify the time in a non-linear and multifractal way. And so what happens is something like that. So this is a paper that we published in 10 years ago or so. So if mu is a Mandelbrot cascade, so I didn't want to put the formulas, right? Because the formulas are a bit tough, but I want to explain what's happening. So the idea that if you combine a Levy process with an independent Mandelbrot cascade, then the sample paths of Y are multifractal. And so what's happening, what's the spectrum? So for a Mandelbrot cascade, the multifractal spectrum has this bell shape, right? And so when you combine the Levy process with this time change, the multifractal spectrum that you obtain is something which is first linear and then strictly concave. And so this case is quite interesting because when you're dealing with the multifractal properties of such objects, there is a competition between two behaviors. On one side, you have the Levy process with the jumps, and on the other side, you also have the irregularity of the measure. And so you have this combination between two properties that you need to analyze very carefully. And of course, when you are interested in that, then the theorem that I mentioned before does not apply. The ubiquity theorem, because the initial assumption is about the Lebesgue measure. on the of the balls. And now if you change time, the balls, they are not uniformly distributed anymore. So you need another theorem that deals with the heterogeneous distribution of the jumps. Okay. Another example, it's Markov process solutions to SDE. So it's work that started maybe 15 years ago, and that somehow finished with the work of Xiaoshuan Yang. We will talk about this maybe at the end of the week a little bit, right? So you consider this stochastic equation, so M of t, and so yeah. And here it's a drift, but you also have so this part is the most important where n is a compensated Poisson measure, right? You have jumps, and of course since there is an m also here, essentially the intensity will depend on the trajectory itself. Okay, so I give here essentially the assumption about g. G, it's z to the 1 over beta x g of x, and you see that here essentially beta depends on x. So it means that this process, essentially the main idea is written here. So m locally around each time t, it behaves like a sort of Levy process of index beta m of t. So it's not exactly, it's more than an intuition actually. For some processes, you can prove that the tangent process at t is exactly a Levy process of index beta m of t. And so what's the result for this? So I put the theorem, but I mean, to understand the formula, it may take a few minutes, so it's better to look directly at the picture here. Okay, the main important result is that the spectrum, the multifractal spectrum, is now random. It depends on the trajectory. For the two preceding examples, the spectrum was deterministic. It was the same for almost every trajectory. Now the spectrum here depends on the trajectory, and the slope essentially are given. The slopes are given by the value beta m of s. And so it's the study again. It's quite tricky because now of course initially you have a random measure with the points that are uniformly distributed, but since the parameter beta essentially is evolving in time, again, you have to analyze more carefully the distribution of the jumps to be able to analyze the regularity of this process. And again, a new ubiquity theorem is needed. Oh, okay, so for the three examples that I gave, essentially the three examples that I gave are based on contain jumps. So what I want to say with the so I'm missing a lot of references are missing. So I'm sorry again. And it's also possible to build multifractal processes without jumps, right? But still the same ideas are apply essentially. So for instance, here is a more recent result. So I fix psi, any function. So it's called a pulse. So Mandelbrot used this denomination, right? And what you do is that, so you sum infinite copies of psi, right? That you essentially, so you xn is say uniformly distributed. So you randomize their location. And also Bn, so and Cn are Poisson processes that tend to infinity. So Bn contract the functions, and Cn to the alpha, it contracts in time and in value. And so I have two parameters, alpha and eta. So you see, since psi is continuous, and essentially this series will converge uniformly, you will get a continuous process here. And there is no discontinuity, right? It's a C alpha over eta process. But using the same ideas as before, we can prove that this series has a multifractal sample path, and there is also a multifractal spectrum. So that does not touch zero. So it starts here and here. So it tells you that for this process here, all the regularity exponents are less than 1. So it's never differentiable. But it's also at least C0.4, something like that. And there is a whole range of exponents that we control. So we know that. This kind of sum of pulses were used by Mandelbrot and many people when they tried to model the rainfalls and so on. Okay, and here, so there is no jumps, but here to analyze this, we need wavelet techniques. And again, refinement is quite needed because we need to understand how well isolated the points are. Because if you draw random points, uniformly random points in the interval, actually they are not isolated. It's highly likely that 2 of them are very close. And so we are very interested in points that are isolated from the other ones. And so what I really want to emphasize on these examples that each time we have a theorem, then also we need another theorem, a companion theorem that helps us to analyze the situations and the pointwise regularity. So, and these theorems, they apply not only to random points, but also to deterministic points. Do I have 1 more minute? Yes. Okay. Great. Okay. And I finish with something which is related, but not really, with the things that I've gave before, because these are the spectra that I showed you. They all have the same shape, like a straight line or even straight line and then something concave. Okay. But what we can observe in reality, because we have algorithms that are able to estimate the multifractal properties, multifractal nature of data. And what we always observe is that there is, for data, for real objects, not the spectra that we observe are strictly concave with a decreasing part. And here we always obtain the same kind of shapes, increasing spectra. And it's also the case, I cannot mention it, but for typical functions in functionals in Sobolev spaces or in Bezoff spaces and so on. So there is a sort of dichotomy because between what we obtain in theory and what we observe in reality. And so that was called the Frisch-Parisi conjecture. Parisi is the Nobel Prize in physics this year, which was this conjecture. So if you take any concave map, there is a function space. Are there function spaces in which typical functions have the shape that we observe in reality, right? And so this is a theorem that we proved last year. So we are able to build a function space in which essentially typical functions have a concave shape. And this is very natural, but and we are able to work in this functional space, in these function spaces, but what we don't know yet is how to build stochastic processes which have these typical shapes that we observe in reality. So this is a challenge for us. Thank you.
So thank you very much for this very interesting talk. And I would like to ask the audience for questions and comments. Anyone?
You mentioned that the model for random sum is controlled by two-dimensional Poisson process CNBN. Any chances to control distribution of homogeneity function, or do I do so explicitly with this sum? Do you have any kind of explicit formulas for homogeneity function or anything in this direction? Function F, yes.
So for the
yes, the random sums were controlled by two-dimensional Poisson process.
Yes, yes,
okay.
yes.
What you can say about distribution or homogeneity function or anything in this direction? Thank you.
So What can I say about the
Well, distribution of all this sum, yes, the whole.
of the
Yes, distribution, yes,
of the values of f of t?
Model, generalization of well-known short noise model, you know, of course, and it's better to have something explicit about this.
No. We don't have it. I mean, what we can say that these processes, they have like stationary increments, for instance. Okay. No, but no formulas. No, not yet, but that would be interesting.
Thank you. Some more questions, comments? Vasily?
All right. Yes, so just a quick one. So I would like to know you mentioned that in the last slide about the you want to build a stochastic process with fixed spectrum, with given spectrum, and so you can sort of do the modified version of a cascade and to have this concave shape, right?
Yes, but actually with the cascades, most of the time the concave shape must be analytic or C1.
Ah, okay.
Okay, so if you want to reach all the possible shapes, it includes also the ones which are not differentiable at some point. I mean, when there is a non-differentiable point in the spectrum, usually it refers to a sort of phase transition in the physical phenomenon which is underlying. So it's important also to have this kind of things in mind. But so I don't know yet how to do that.
Yes, please. Yeah, very nice talk. Thank you very much. You present this discrete spectrum if Markov process is given by stochastic differential equation.
Yes.
If I give you a generator of a Markov process, can you tell me something about the spectrum?
I would like to. I think a more systematic study of given the generator, what can I say, would be very nice to do that.
Still not exist. Yeah.
Still not exist.
Thank
you. But yeah.
Anybody else? Yeah. For the virtual participants, if you have not raised your hands, which I do not see, you can unmute yourself and ask a question. I believe there are no questions virtually.
So, are there any more questions, comments here? I don't see. So thank you very much. And thank you very much, the speaker, again, for a very interesting talk.
Thank you.